In this chapter, we're going to be talking about probability. I read somewhere where an author said that probability is the science of uncertainty. And actually, as probability is used, it turns out that a probability is a number, and it is a measure of the likelihood of the occurrence of an event whose outcome is unknown. Now, probability has a certain vocabulary associated with it. Let's go through some vocabulary items, and then we'll get right into measuring or finding those probability measures. An experiment is a happening whose result is unknown. Now, that kind of definition is not something that you need to commit to memory. You'll understand the nature of experiment by some examples that we talked about. An example of an experiment would be rolling a die. You see, rolling a die is a happening whose result is unknown. We don't know the result of this rolling of a die. A die has 6 sides, and we'll be talking about 6-sided die as we discuss it here in this situation. And the die has on it the various faces. The 6 faces have a 1, a 2, a 3, a 4, a 5, and a 6, as you probably already know. But the result of rolling the die, we don't know the result of that, but that's the experiment. Okay, the outcomes are the results of the experiment, so we don't know the outcomes of that experiment. Sample space would be the list of all of the possible outcomes for the experiment, and all of the possible outcomes for rolling a die would be 1, 2, 3. You see, and when we roll the die, we could get a 1, we could get a 2, we could get a 3, and so on. So we're listing all of the possible outcomes here in our sample space. An event is some subset of the sample space. An example of an event is rolling an even number. So rolling an even number, and 2, 4, 6 would be those even numbers that we're talking about. It's some subset of the sample space. Well, with this in mind, we are talking about an experiment here that has equally likely outcomes. And when we have equally likely outcomes, the probability of some event, and notice the notation here, probability of some event, is just the fraction favorable outcomes divided by possible outcomes. Now, all the possible outcomes would be the number of items that are in the sample space. You see, those are the possible outcomes. And the number of favorable outcomes depends upon the kind of situation we're looking to, the event that we're talking about. Now, for example, the probability of odd. Well, let's see, the probability of an odd number, that's our event here. Now, how many favorable outcomes are there? How many odd numbers are there on the various faces of the die? Well, there are, let's see, 1, 3, and 5. Those are the odd numbers. So there are 3 favorable outcomes. The possible outcomes, the entire sample space, the number of items in that sample space is 6. So the probability of rolling an odd number would be 3 out of 6, or 1/2. Now, probability numbers can be expressed in many different ways. Here we're expressing the probability number as a fraction. It would be okay to express the number as a decimal. It would be okay even to express this as a percent. And in different situations, we're going to use a different form for the expression of the probability number. Okay, but for right now, fine. The probability of odd is 1/2. Probability of 4, well, favorable outcomes. There's only one 4. You see, there's only one way to roll a 4. It's to have a 4 on the top side of that die when it's rolled, and the possible outcomes is 6, so the probability is 1/6. The probability of a number greater than or equal to 3. Well, let's go over, now see, once we get a little complicated with this, sometimes we can look at the sample space. These are all of the possible outcomes. Now we're looking for the probability of rolling a value greater than or equal to 3. Well, that means we could roll a 3, a 4, a 5, or a 6. There are 4 of those outcomes that would fit the prescription for being greater than or equal to 3. So we're talking about favorable outcomes. There are 4 of those out of the possible outcomes, 6. 4 out of 6, that's 2/3 for the probability number. Probability of a 9. Well, let's see. A 9, let's look in the sample space. We're looking at numbers 1 through 6. Is there a 9 here? No. So if there's no 9 here, then the probability of a 9 Favorable outcomes? No way. There aren't any ways for that to happen out of 6. So the probability number is 0. Consider drawing a card, and a lot of our examples here, because of the nature of probabilities, will have to do with cards and dice and flipping coins and such things as that. Now here we're assuming we're talking about a fair deck of 52 cards, and that deck is well shuffled, and we want to know the probability of an ace of hearts. Well, how many ace of hearts are there? Well, there's only one card that is the ace of hearts. So the favorable outcomes would be 1. The possible outcomes would be 52. There are 52 cards in the deck. Probability of a king. How many kings are there? Well, there are 4 of them, 1 in each of the 4 suits. So favorable outcomes 4, possible outcomes 52, and we would presumably reduce here to, let's see, I think it's 1 in 13. Probability of a red card. Turns out that half of the cards in the deck are red. That means that 26 of them are red out of the 52 total cards, and so the probability of drawing a red card is 1/2. The probability of a red ace. How many red aces are? See this, the first question, how many of these things are there? You see, to get the favorable outcomes. Well, there are 2 red aces, the ace of hearts and the ace of diamonds. So favorable outcomes 2, possible outcomes, still we're talking about a whole deck of cards, 52. Notice that the possible outcomes in all of these was 52. 2 over 52, 1 over 26 if we're reducing. Well, from this idea with the cards and the die, we may be noticing that if we're talking about favorable outcomes over possible outcomes, we can't have more favorable outcomes than there are possible outcomes. So in this fraction, in these fractions that we're making for the probability number, that fraction can't possibly be greater than 1. It could be 1, but it can't be greater than 1, and it can't be negative. So it turns out that a probability number is a number between 0 and 1. It could be 0, could be 1. If the probability of an event is 0, it means the event cannot occur, like the probability of rolling a 9 with a fair die. If the probability is 1, it means the event must occur. The event must occur. Now, as we approach 1 with a probability number, it becomes more and more likely. As we approach 0 with a probability number, it is less and less likely to occur. Now, be careful in saying either of these extremes in terms of probability. It would be wise not to use them in practical situations. For example, if we're talking about what's the probability well, one situation where we could use it is what's the probability of me winning a gold medal at the next Olympic Games? Well, that probability is 0. You see, I know that with great certainty. But other things that you do, things that are going to happen, just be very careful. If you're really sure something is going to happen, you're probably not absolutely sure, so use something like 0.9 or 0.95 or something like that. It's almost a 1, but it's not quite a 1. The absolutes are generally to be avoided. Okay. The probability number is between 0 and 1. 1 is must happen, 0 can't happen. What about the probability of a 4 on a die? Now, we talked about it before. The favorable outcome, there's only 1 4 on the die out of a possible 6, so it's 1/6. What about the probability of not 4? The numbers that are not 4s, that's 1, 2, 3, 5, 6. There are 5 of those, so let's see, 5 out of 6 is the probability. Now, notice that the items that we're thinking about when we talk about not 4, along with the item of 4, of rolling a 4, represent the entire sample space. And if we add these two, that is the probability of 4 plus the probability of not 4, we get 1. And that's sort of always going to be the case. If we cover all the bases with the possibilities, then the probability sum would be 1. And indeed, if we add the probabilities of all of the items in the sample space, we're going to get 1. The probability, for example, with the die, the probability of rolling a 1 is 1/6. The probability of rolling a 2 is 1/6. The probability of rolling a 3 is 1/6. And so on, all the way to the probability of 6, which is 1/6. If we add all of those probabilities, we have 6 items in the sample space. Each of them has a probability of occurrence of 1/6. Adding them, we get 6 out of 6, or 1. That's kind of an important feature here. And another aspect of this is that notice that 4 and not 4, the probability of rolling a 4, the probability of rolling a not 4, has a sum of 1. Now that gives us an interesting way of finding not something. You see, if we want to find the probability that something is not going to happen, then we can take 1 minus the probability that it does happen. Because this is the probability of an event and not the event is 1. Now algebraically we can move either of these items to the other side of the equation, you see. We can say the probability of 4 is 1 minus not 4. Or the probability of not 4 is 1 minus the probability of 4. Now, as an example, if we know the probability of some event is 0.7, then the probability of not that item would be, well, it would be 1 minus 0.7, or 0.3. In a similar way, the probability of an event is 15/100ths, then the probability of not that event would be, let's see, 1 minus 0.15, or 0.85. Now I could swap, this could be not E and that could be E. You see, it just turns out that the sum of the probabilities of those two must end up being 1. Consider this problem involving the number of automobiles owned by families in a small town. Here we have the number of cars owned, and here we have the number of families that own this many cars. So this is a column of x's, and these are frequencies then. So to interpret the chart, we're thinking that there are 1,767 families that have 2 cars. This many families have 3 cars, this many have 4 cars, and so on. Okay, now with that in mind, in this frequency environment, let's think about the probability that a family would have 3 cars. Well, let's see. This many families, 1,107 families, have 3 cars. The probability, if we were going out and selecting a family at random, the probability that that family has 3 cars would be, let's see, favorable outcomes, possible outcomes. You see, the total of the frequencies is the total number of families in the town. So if we're choosing a family at random, then it's favorable outcomes over possible outcomes. So to make the calculation then, we would come out over here to the side. For a family selected at random, the probability of 3 cars would be 1,107 over 4,000, or this decimal. Now, there's another interpretation of the situation, though. It turns out that when we have used tables that have frequencies involved, we talked about relative frequency. And what we have done here is just calculated a relative frequency. In fact, I have made a relative frequency column here, and these can be thought of then as probabilities associated with the number of cars for a family chosen at random. That is, the probability for that a family chosen at random will have only 1 car in the family would be 877 over 4,000, which is the relative frequency associated with this row, or it would be this number. So now we're thinking now, and I think the point here is that we can make the calculation of probability in a different way besides the formula. It can emerge as a relative frequency number when we're talking about this column arrangement and frequency arrangement that we have discussed so many times before. There's another situation that can come up that really doesn't apply to the formula, and that's it's kind of an intuitive or an intuition kind of probability. It's the kind of probability like I was talking about earlier when I was discussing the probability of me winning a gold medal at the Olympic Games. That probability is 0, and that's just by intuition and just sort of the facts involved. Well, what if we were talking about something that wasn't so assured? What about something like the probability of going to church this Sunday? And we might use some intuition for figuring this probability. We might say, well, gee, my family goes to church just about every Sunday whenever we're in town. We don't have any plans for this coming weekend, so barring an accident or something coming up at the last minute that's really unknown to us now, we're going to definitely be in church. So there's a high probability of going to church this Sunday. We might assign a number to that probability as 0.95 or 0.90, something like that. You see, at the high end of the probability scale. And this is assigning a number by way of intuition, using the facts involved in the situation. So we have actually 3 ways to assign probability numbers, and one of them, the first one we talked about, was by using the formula, favorable outcomes over possible outcomes, and another is using the relative frequency number involved in the chart arrangement, and the third way is by intuition. John runs a computer software store. Yesterday, he counted 127 people who walked by his store, 58 of whom came into the store. Of the 58, only 25 bought something in the store. Let's understand what the problem says by outlining some information. It says that 127 people walked by the store. All right, then out of that group, it's saying that 58 came into the store, actually entered the store. And then of that 58, 25 of those bought something. So 25 of the 58 bought something. Let's use the outline now and answer a few questions. First question says, estimate the probability that a person who walks by the store will enter the store. We can figure the probability of entering as favorable outcomes over possible outcomes. Favorable outcomes, well, let's see. The numerator would be those people that actually came into the store. Well, 58 people came into the store. The possible outcomes would be the people walking by. 127 people walked by. We turn this into a decimal, and here's our probability number. Next item says, estimate the probability that a person who walks into the store will buy something. A person who walks into the store will buy something. We start the same way, and now we're figuring the probability of buying. Favorable outcomes would be the number of people that buy something. 25 people bought something. Now, the trick here is the possible outcomes. The sample space here for this part of the problem involves identifying the people who walk into the store. You see, it says estimate the probability that a person who walks into the store will buy something. The people who walk into the store, gee, that would be 58 people that walked into the store, you see. So the probability number 0.43. Estimate the probability that a person who walks by the store will come in and buy something. Now I'm going to give you a peek into the next section here. We haven't talked about this before, but the word "and" has a rather particular significance to us in statistics and in calculating probability. And I'm going to write the probability like this. The probability of entering and buying. The probability that a person chosen at random will enter and buy something. And it turns out that when the word "and" is used, we often multiply probabilities. And in the next section we'll see how this is done a little bit further, but the probability of entering times the probability of buying something given that they entered is the way this problem will be worked. Now the probability of entering, let's see, 58 of the 127 came into the store, so that's 58 over 127. Now the probability of buying given that they entered, we figured it before in part B, it's 25 out of 58. And now it's an arithmetic calculation. The 58s cancel, and then we multiply straight across to get our decimal value. Of course, another way to calculate the problem is to calculate favorable outcomes over possible outcomes. And we're talking about entering and buying. Now, the buyers are the 25 people that bought something. The possible outcomes are the people that are walking by the store. So it's 25 over 127. We get the same probability number, 0.20. The last part says, estimate the probability that a person who comes into the store will buy nothing. We can actually calculate the probability of buying nothing in a rather offhanded way. Think about the probability of buying nothing as 1 minus the probability of buying something, you see. And the sample space involved has to do with the person who comes into the store. We're limiting our sample space to people that come into the store. And it's really important to identify sample space every time we figure a probability number, because that sample space is often the denominator of a fraction that we're writing. So the probability of buying something, given that someone comes into the store, is going to be the 25 out of 58, the 25 over 58 number that we calculated before. So this is 1 minus 25 over 58. 1 is 58 over 58. And subtracting here, we get 33 over 58, or 0.57, as the probability that a person selected at random from this group will buy nothing.